Okay, I've started the local recording, and the Zoom also is
Okay.
the Facebook feed is, I think, 2 more seconds.
You're permitting me to share the screen, right?
Yes, you are allowed to share the screen. So.
Okay.
Mm-hmm.
Do you want me to try that?
Yes.
Or not yet?
Sure. We can.
Yes.
Yeah, we can.
Okay.
Oh, there we are.
Yep. So I think we can start.
Okay, great. Well, welcome back everybody and everyone watching us live on social media to our first annual mini Atlantykron days, where we bring a different topic that we focus on to you every month with special guests and experts in the field to talk about that topic and our future. So we want to welcome Peter. Thank you so much for being here. I want to turn the mic over to Corneliu to introduce you, and thanks for being here, everybody.
Thank you very much, Heather. And I would like to present Professor Ottensmeyer. He is a great champion for the nuclear industry and also to recycle the spent fuel. He dedicated his life teaching a generation of people in the University of Toronto, one of the largest university in Canada. So, and he is one of the great champions for recycling the spent fuel and to provide new energy for the future. So, Professor Ottensmeyer.
Thank you, Cornelio, and thank you for the invitation to speak with you. It's a real pleasure, and I should say that I am not brought up in the nuclear field. I'm a cancer researcher with a background in engineering physics, so I can understand it, but I'm not really sort of a dyed-in-the-wool expert. I took it up as a hobby, my wife says, after I retired. And it's become a passion, and I think it's the future of the world if we do it right. And part of this is recycling. Let me just get my pointer up so that you can see it permanently. It's recycling of our what's called nuclear fuel waste, but it's not really waste. And to put it in perspective, energy is one of the most important things that we have in order to live. And I'm going to talk about that, the past, way back, and then 2 centuries that are important that cause all the difficulties that we have in terms of climate change potentially today. And then I'll talk about the future. And that'll be sort of lighthearted. But then we'll get into some of the more serious stuff, the recycling, and I hope you'll stay with me. I'll try to make it easy to understand because it's not, nuclear is not very difficult at all. If you've played billiards or pool, then you know half of nuclear physics right there. You have a feel for it. So let's start. The United Nations puts out graphs where they compare countries with the amount of energy they use in oil equivalent kilograms here versus the earnings that they have. So you might say this is pleasure and this is the work that's applied. And you notice that the more energy you use, the higher your standard of living. So Norway, takes the cake here. They're doing very well. Canada's up there. I don't see Romania down here. I guess you're not important enough to the United Nations. There are other nations, and you find that if you struggle to use more energy, then you actually do better. And so the red dots here are around 1980, and the blue dots are around 2000, 20 years later. And you notice Bangladesh moved up that line. And so did Malaysia, and so did Singapore, and even the United States up here did better the more energy they used. And so energy is important. It always has been. we started out way back when we were cavemen just using our muscle. That's the only energy we had. And then we found out that animals actually have stronger muscles than we do, and that increased our standard of living right there. And then we invented simple machines to increase the efficiency. We found that ramps are better than just, and we have levers and wheels and winches and blocks and tackles, and that really made life a whole lot easier and more productive, so that we can use more energy and have more pleasure. I particularly like the invention of the block and tackle because it brings me back to my sailing days. And sure enough, with that, we invented ships and windmills and water wheels and so forth. And all of that really is solar energy that we're using because wind comes from there, and the water, of course, gets evaporated and then comes down as rain. And it made life a pleasure as well as being able to explore other countries. This just sort of warms the cockles of my heart to imagine myself going over oceans under wind power. It's terrific. And we used wind power, to drive grinding wheels and so forth for flour. We used water wheels to drive machines and turn grindstones and so forth. And that's as far as we got. And you might say that is the era of what you might call an era of carbon neutrality, because there essentially we didn't use any excess carbon energy at all. Whatever we used was wood, and it would grow again, and we would use it. The wind, of course, is solar energy and so forth. And so that ended somewhere around the end of the 16th century and so forth, in the beginning of the 18th century. And what ended it really was the invention of the steam engine. Because then wood wasn't enough anymore, because that steam engine really required a tremendous amount of fuel to run it. And that fuel was coal or oil, and still is natural gas and so forth, and it provides heat and it emits carbon dioxide. But of course, then we were independent of the wind. And then we invented the internal combustion engine, and that really took off. Because we not only were able to move around at slow speeds and then faster speeds if you have Lamborghinis, or you lift yourself off the surface of the earth and go flying at great speeds. This is the supersonic plane there. I never had a chance to fly. My wife said she would love it because it only takes 2 or 3 hours to go across the ocean with that. It's wonderful. And then we invented electric motors, and you figure, well, those must be very efficient and good and this sort of thing. Well, they are if you have hydropower, but most of us don't. And so we use coal and oil and natural gas again to create electricity. And so you can ask how much carbon dioxide have we emitted into the atmosphere since the beginning of the industrial age? And actually it's a tremendous amount. This is the world line here in green, and Romania is way down there, so you're okay. Canada is a little higher. China is, while they have more people than most anybody. And so obviously they use more carbon energy. But the importance really is the total that has been emitted since the industrial age. And that by now is almost 2 trillion tons of carbon dioxide that we emitted. Now, is that a lot or is that a little? Well, if you take all of the carbon dioxide in the entire atmosphere around 1800, that was about 2 trillion tons. Now in 2020, it's about 3.1 trillion tons. And you say, well, what happened to the rest of it? Because 2 and 1.8 should be close to 4. Well, it turns out that some of it ends up in the ocean. And so it's acidifying the ocean, and 45% of all of this carbon dioxide is in the ocean. And since I scuba dive, that's worrisome, because the corals are starting to bleach with ocean warming and the acidity of it. And so, is this serious or isn't it? Because carbon dioxide levels have gone up and down way back, over 1 million years, even before that. And, man got out of the trees some 2 million years ago, and he got some wisdom, supposedly some 200,000 years ago. But we survived all of these fluctuations. But right now, the fluctuations are way higher in terms of carbon dioxide. And so that's sort of worrisome, because if the temperature sort of follows this trend roughly, then we should be aiming towards about 15 degrees warmer than where we're now. And that's pretty warm. Well, maybe for the north of Canada, that's okay. But for the rest of the world, that's not very nice. Well, right now, over those 200 years, we've only warmed about 1.2 degrees, but it's still going up. And so we should do something. And the Germans invented a new word called the Energiewende, or energy transition. But I don't think they really did too well. They said, well, we're going to use solar panels and wind turbines, which basically is nuclear fusion from the sun, that energy. But their carbon dioxide emissions really haven't gone down substantially, even for the trillions of dollars that they invested in in this process. The energy transition that's really meaningful is one that requires nuclear fission, nuclear energy. And if we look at that, by now we've got about 450 reactors in the world, and what have they done? Well, we've mined about 3 million tons of uranium, but surprisingly, we've used less than 1% of that uranium and split it and got the energy from it, only about 16,000 tons. And that's produced about $11 trillion worth of electricity. And it's avoided the emission of 90 gigatons of carbon dioxide. Now, it sounds like a lot, but it's about 3% of the carbon dioxide in the atmosphere, which is a start. But imagine if we use the rest of the uranium, which we now call used fuel or depleted uranium. There's still 295 million tons just sitting on top of the Earth. It's been mined already, and it's there. And that would avoid the emissions of about 17,000 gigatons of carbon dioxide. Now, compared to how much is in the atmosphere, that's about 5.5 times what's in the atmosphere. So it's huge. So that's really a direction that we go in, and we've already mined and got this uranium sitting around. But how do we do it? Well, basically, we have to recycle this material through what's called fast spectrum reactors. The ones that are popular right now in the news are small modular reactors, and even Romania is building one of them. So by recycling, I consider that to be a form of nuclear waste management. And I'll go into that. This closes the fuel cycle. Now, I'm going to use a few technical terms here, but I'll explain them. Because right now, we're not closing the fuel cycle, even though it's called a once-through fuel cycle. What that means is that we take the uranium from a mine, we take the ore, make fuel out of it, and we put it into a reactor. In Canada and in Romania, we use CANDU reactors, and so we'll put it into a CANDU reactor. After a while, it comes out, and it's very slightly used fuel. but it's very radioactive, and it will remain that way for about 400,000 years. Now, the containers that we have in Canada look like this. In Romania, near Chernov Voda, you've got these concrete containers sitting outside of the reactors, but it's the same sort of idea. And the radioactivity in there won't go away for about 400,000 years. So obviously, the world is thinking that what we should do is take that and put it into what's called a deep geological repository. That doesn't change the used fuel at all. It's still going to be radioactive for 400,000 years. And you sort of worry about what happens. So the idea really, since this is only slightly used fuel, is to recycle it. What does that mean? Well, you take the slightly used fuel and you shake out the ashes. Well, the ashes, like in a fireplace, for uranium are really split uranium atoms called fission products. And they don't have very long lived radioactivity at all. So only 2 of them have 30-year half-lives. All the rest of them are shorter than that. So it's nowhere near that 400,000 years for the entire thing. Now you take that fuel and you put it back into the reactor, except you know, for a CANDU reactor, that's relatively expensive to do because you've used that fuel already. But these small modular reactors or fast spectrum reactors just love this material. And so you can recycle it and you get much, much more energy out of that fuel. You use that fuel and it's actually practical because the technologies to do this exist, and I'll talk about a couple of them. And it's relatively cheap. Now, nothing in nuclear is cheap, but you know, that's why I say it's relative. And for most countries, the funds already exist because nuclear is one industry which actually puts money aside as it produces electricity in order to take care of the used fuel that's there. So the funds exist to do this. And what I love about this is that it's very effective because it actually eliminates the million-year radiotoxicity of the used fuel. Now that's really wonderful. So let's explain this in some detail so that you can talk intelligently with your neighbors. And let's start at the beginning. The uranium that we use is put into fuel bundles like this, and the uranium itself has 2 different types of atoms. One is called uranium-238, and there's 99.3 of that. The other one is called uranium-235, and that is sort of like the kindling, whereas this is sort of like the heartwood if you talk about logs, and that's not 100%. So we take this log of used fuel, put it into the CANDU reactor, and about a year later, it comes out, and the uranium is still mostly there. It's been changed very little. The U-238 goes from 99.3 to 98.6, so you've used about 0.7%. The uranium-235 goes from 0.7 to 0.2, and there's, it makes some U-236, so you actually use about 0.4 of it. So you use very little of this. Some of the uranium-238 becomes plutonium of various types, and then americium and curium and so forth. And some of the uranium is split into fission products. Now, it's a good thing that these so-called transuranics, these things that are heavier than uranium, are produced because we only get about 50% of the energy in the reactor from uranium directly, whereas the rest of it comes from these transuranics. Now, I've used these terms, so let me explain them. You probably remember that chart that was on the wall of your chemistry class. You know, it's got the periodic, all of the elements in the periodic table are there, from hydrogen, which is the smallest atom in the world, to uranium, which is the heaviest atom in the world, natural atom. You know, uranium is called an actinide because it's in this chemical row right here, and that chemical row starts with actinium. So actinides are nothing except these atoms that are start with actinium. These would be lanthanides that start with lanthanum. Now, there are no natural atoms heavier than uranium, but we create them in the reactor. And those atoms here that are heavier than uranium are called transuranics because they're on the other side of uranium. And then there are fission products. Well, what are those? Well, if you split uranium exactly in half, it has atomic number 92, half of that is 46, you would get palladium. So you get 2 palladium atoms for a split uranium. So that you know, it's a perfectly natural atom. So fission products are just normal atoms. If you're very good at cleaving logs, then you can split them exactly a half, but I'm not. And so neither is the neutron in the reactor. So you split the thing about one half is a little larger than the other. And so you get all kinds of medium-sized atoms of the in the periodic table that are created in the reactor. All of those are fission products. Now, if you're Paul Bunyan, one of our mystic lumberjacks in Canada, then that's okay. But if you're Superman, then you go looking for krypton, which is over here, and it's half of the log is over there. That's barium. So even Superman can be happy with cleaved fission products. So you know what fission products are. Perfectly normal atoms. Some of them are radioactive, most of them are not. But what's surprising is that we've only used less than 1% of the uranium. And you say, well, that's not, shouldn't give you very much energy, but it does because it's nuclear energy. And that's tremendously powerful per atom, about 40 million times more energy per atom than you get out of burning carbon. And since 1970, we've created about 4,400 terawatt hours of electricity. I don't know how big that is. I know billions of dollars. It's basically created $440 billion of electricity and avoided the emission of 3.8 billion tons of carbon dioxide. Now, those are pretty impressive numbers, but imagine if instead of the less than 1%, we used all the rest of this and created energy. That would give us 130 times more energy from our used fuel. So that would give us 600,000 terawatt hours of electricity, or $60 trillion worth of electricity. Oh, I just lost my signal over there. Okay. Can you still hear me? See me?
Can't see you, but we can hear you.
Yes,
we can
yes,
see
we
you,
can.
but not your screen.
I wonder what happened.
But we can hear you.
Yes. All right, let me try this. My screen doesn't respond.
Is there a way to stop screen share and then start it again?
Okay, that doesn't respond either. I may have to.
The screen share stopped. I think maybe it's have a bit of delay taking the commands.
Yeah, but I don't see anything happening on my screen. I may have to just reboot the computer.
Okay.
Or just exit and try to re-enter the meeting, maybe, to work.
Hello?
Yes.
We can still hear you and see you.
Okay.
So.
But nothing happens here. nothing responds on my computer.
Do you want to restart your computer?
Well, I was trying, but I can't even.
Okay. Technology. It's wonderful when it's working. We'll get it back up. Very, very interesting. Topic. So I'm looking to see while he's kind of rebooting what countries we have here. I know we have Romania. I know we have Nigeria. I know we have Aruba. Oh, I know. I'm trying to see. Maybe everyone can type in their country. Where are you here from? I think we have 6 or 7. And thank you, everyone.
Share screen. And
Yes.
go to there. And I just have to remember where I was, right?
Yes.
Nice to have you back. We were all just chatting about computer glitches.
Yes.
They happen.
Okay.
So you were
I think
Transuranics.
I think I was probably
About right
around
there.
there, about there. No.
The periodic table, Peter.
Yeah, and Mihai, we can go back to our
Yep.
live. Okay.
Okay. Well, oops. So let me go back.
So go down to the periodic table, Peter.
I'm sorry?
The periodic table when you speak about Transuranics.
No, let's see. What did I talk about getting 130 times
Yep.
more energy? So
Yeah.
that's right about there.
Okay.
Okay. So how would you like me to start? As though it's I'm at the beginning of the slide.
Sure, that sounds great. We'll pick up there.
Okay. Anyway, I'll apologize to whoever was watching and got cut off so unceremoniously. We were at a point where our Canadian nuclear waste could produce 600,000 times more terawatt hours of electricity, or 60 trillion times more dollars in terms of that electricity. Now, that's a lot of money. If you divide that by the population of Ontario, that's $4.1 million per person in Ontario, or for Canada, that would be about 1.5 million per Canadian. You can multiply that by 3 and you have your Leos in Romanian money. That's a lot of money. And we would save 500 billion tons of CO2 emissions. That's 16.3% of all of the atmosphere, and that's just Canada. So I think that's really worthwhile going after. So how would we do it? Well, I gave it away already when I talked about small modular reactors, and Romania is working on one of them. Here are a whole series of them because they're becoming popular in the ideas of people in nations. Here's your own Alfred right there. I like a prism reactor and so forth, but you can have your choice. If you look at them, they come in all sizes from 4 megawatts up to 300 megawatts, which is sort of the limit of what is called a small modular reactor. What's impressive about them is that all of them require enriched fuel, whereas the CANDU reactor can work on natural uranium with this low concentration of U-235. And so that's really a difficulty with these reactors, certainly for Canada, because Canada doesn't have enrichment facilities. Romania probably doesn't either. So we have to rely on friends, friends that normally produce nuclear weapons, because if you have enrichment facilities, you build them because you want to build nuclear weapons. And then if you have excess capacity, you sell some of this stuff. So we have to go to Iran or India or Pakistan or North Korea or whatever, or some more friendly countries like France. Well, China at the moment isn't too friendly, Russia, and the USA. But even the USA, has a border between them and us. And so is that a dependable supply? Because the USA embargoes our aluminum and steel, and it cuts off our oil lines that are running through the United States from the west into Ontario, the province. And we're under threat of losing that in May. So that's what borders are about. But it turns out that we actually have our own fissile fuel material. And you say, well, we don't have enrichment facilities. Well, but we do have this used fuel, used CANDU fuel. And while we can't get at the U-235 as the kindling to start these reactors, we can chemically get at the plutonium, which also has fissile material in it. And you say, well, it's only 240 tons. Well, remember, uranium is very rich in energy. So that would actually start reactors with a total power of about 24,000 megawatts. That's more than twice the total energy that we have in nuclear in Canada right now. And so it would start maybe 800 of these reactors or 6,000 of these smaller ones. So that is actually very valuable. And if we choose the right kind of reactor, which use fast neutrons, including your own Alfred, then those reactors, once they're started, can actually use the rest of the uranium as replenishment. So all of this material becomes good fuel for thousands of years. And it's all non-carbon energy. So how do we go about this? Well, we separate out this material, but it's difficult to make that pure because then you say, well, you can make bombs out of this material. Well, no, you can't, because it's a mixture. But still, you can purify the uranium quite nicely. You can purify the fission products quite nicely. And then you have an impure mix of everything else here. And that is actually very useful as starting material for these small modular reactors. Now, there are umpteen separation methods. I looked it up and there's 50 of them, but I'll talk only about 3. One is sort of a chemical affinity separation. The next one is an electrical affinity separation. And the third kind separates things on the basis of changes of state from solid to liquid to gas. And so they all work. We actually use 2 of these methods already in Canada. The company called Cameco, it mines and refines uranium for the world, including for CANDU reactors in Romania, I'm sure. And Alcan, for instance, uses aluminum refining, which is electro-refining, which is this particular process. So internally, we have expertise that can do this. And then, of course, these people that want to bury the material in deep geological repositories will tell you that, no, it costs a bundle to do that. Well, let's find out. Since it's going to be large numbers, let's divide that by the number of fuel bundles that we can actually handle, and that gives us numbers that we can deal with. We have to buy land, we have to construct material, it has to be shielded, and maybe robotics. The worrisome things is the license, because bureaucrats love sitting on things, and that costs time. Annual costs, of course, operating and maintenance, and you have to pay for the administrators. You have to pay for taxes, and you borrow money, so it costs you interest to pay for that. All of that goes into the equation. Now, modified Purex is a chemical technique, and so it's umpteen chemical reactions that I won't go into, 16 of them here. And the Koreans actually have each of those reactions in a separate building. And so this costs a lot of money. This is Purex that was developed by the military, and the military usually don't care what it costs. So obviously it's expensive. It costs about $7,500 per fuel bundle to separate out those three fractions. Pyro processing is a whole lot simpler. What you need is a bathtub full of sodium chloride, that's table salt, and some potassium chloride, which is a substitute for salt if you have a heart condition. So it's cheap materials. You melt that at 500 degrees, and you make it an electrolytic cell by putting one electrode in there, which has impure used CANDU fuel or other fuel in it. You need a small battery. 3 volts will do it, except of course it has to be a pretty large 3-volt battery. Then you put in an iron electrode here, as well as a cadmium electrode, because the chemicals react differently even with electricity. And so when you turn on the iron electrode, it dissolves the uranium and plates it out as pure uranium on the iron, and the fission products sort of stay in the vat. Then once you've sucked out enough uranium, you change the electrodes to cadmium, and they get the transuranics, the plutonium and so forth, and the rest of the uranium there as a mixture. And that's a safe mixture. You can't build anything out of that in terms of nefarious explosives. And so you're ready to mix the transuranics with the uranium in the right proportions for it, depending on what reactor you have. And it's a small operation. When I said a bathtub, well, maybe a hot tub is more like it. And that's big enough for 4 of these sets of electrodes to put in there. And if you need more, well, it's modular, so you just add more as you go, depending on your reactor. And it's small in size, and there are very few residues left over, which is very nice. And it costs less. It's about 1/6 of the price of the Purex military approach. Fluoride volatility is what we use in Canada already. Cameco makes uranium oxide for CANDU reactors, and for the rest of the world that has to enrich, they turn that into gaseous uranium hexafluoride in 2 stages. First of all, because it's cheaper that way in terms of fluorine. And all you need then at the end, once it's fluorinated, is a condenser. If you've ever made alcohol out of mash, you know what a condenser is. It drips out the uranium hexafluoride as a liquid, and you cool it some more, and it becomes a solid, and you can ship it quite nicely to various countries. Now, if you use used fuel, it's exactly the same procedure, except you need more condensers. So it's not all that expensive. You need them at different temperatures, so 100 degrees instead of just 40, and at -15. And also you extract it here at higher temperatures. And the first stage, you fluorinate a little bit, and it gets all of the uranium, or most of the uranium, out as uranium hexafluoride. And then you fluorinate the rest of it, and use all of these various condensers. The transuranics come out in the same 40 degrees, but the fission products come out at various other temperatures, and some of the transuranics come out at very high temperatures as well. So it's a simple procedure. It's small in size and low residues as well. And it's also inexpensive, about the same as the pyro processing. So if you're a chemist, maybe you want to go in this direction. If you're a physicist, then you're probably happy with this. You can do it. Now the question is it actually cheaper to do this rather than to just keep the fuel bundle intact and bury it? Well, I mean, burying costs money. And we've been putting money into the burial process. By now, we've got about $10 billion there. And at that time, that was for the order of 2.7 million fuel bundles. So per fuel bundle, we're putting about $3,600 into the pot to bury it and get nothing in return. And that actually is sort of partway in between the prices that you've got for the various techniques. So if the nuclear waste people say, well, it's too expensive to process, they're right, because if you compare it to this Purex military approach, it is cheaper. But if you consider pyro processing and fluoride volatility, it's cheaper to do that. And you get stuff back out, energy. But that's still not fuel for the reactors. So the question is, can you make economical fuel for the starting fuel for these reactors? If we pick pyro processing as the middle technique, and we have to now pick one of these reactors, it doesn't really matter which one, so let's pick one of the larger ones. It requires 20 tons of fuel at 15% enrichment. Well, 15% enrichment comes not from 3 tons, but from about 4 tons of transuranics, because they're not pure fissile starting material. Now, 4 tons is a bit more than a single fuel bundle. From a single fuel bundle, we only get 80 grams of these transuranics. And so we need a lot of fuel bundles, 50,000 to start this particular reactor. And that cost us about $70 million. Well, that's more than I earned in my lifetime. But if we compare that to trying to buy the 15% enriched fuel, say from the United States, here are a couple of sources. They both cost about $150 million to do that. And so you might say going in the recycling direction is actually less than half the price of buying the thing. And it's within our country. We've got control of that. So nobody's got a border that will cut us off from a future energy supply. So that's a good thing. The other thing, of course, that I liked at the very beginning was the fact that you eliminate the long-term radioactivity. If you recall, the fuel bundle is handled by people. In other words, it's not very radioactive at all. But once it comes out of the reactor, it's about 1 million times more radioactive than it was going in. Now, the lovely thing about radioactivity is that it decays. And so the fission products decay with time. And this is 1 month, 1 year, 10 years, 100 years, and so forth. And the oldest used fuel that we have from our Pickering plants in here, right near where I live, is about this old now. And so the fission products have decayed to this level here at the bottom. And the radioactivity really will not decay any further because it's now determined by the transuranics that are in the fuel that are made in the reactor. And the transuranics will stay about the same for about 10,000 years before anything happens that the radioactivity decreases. But remember, this stuff, the transuranics, are lovely starting fuel for all of these small modular reactors. And so we can take this material, put it into the small modular reactors, and it's gone. So the million-year problem is gone. We still have the fission products there, and we have the recovered uranium, which isn't very radioactive, but it's useful because if we choose the right type of small modular reactor, called a fast spectrum reactor, like the ARC 100, the PRISM, and so forth, including your own Alfred, then they can, their fuel can be replenished with this recovered uranium. And so you use that and it's fuel for centuries. So that's very useful. And so we've got the fission products left, which will decay away. And by this point, they're less than the original uranium that it came from. But remember, these fission products are perfectly good atoms all the way in the periodic table here, all over. And you notice this middle is silver and palladium and rhodium and ruthenium. These are platinum group metals. They're valuable. So if you line them all up and find out how much you've got and what they would cost if you bought them, the amounts are in this lower curve here. And so some of them are tons and some of them are 1,000 tons, some are 10 tons. Palladium, for instance, is about 40 tons in this 50,000 tons of used CANDU fuels converted to fission products. But look at the value, it's almost $1 billion right there. So you don't want to throw that away. And ruthenium and rhodium are non-radioactive right away. So if you're a smart chemist, you can extract those. In the Pickering fuel, we only had 2 fission products left that are still radioactive. That's strontium-90 and cesium-137. And those, a chemist tells me he can easily extract them. So the rest of it is all non-radioactive, useful stuff and valuable at the order of $3 million per ton. So depending on how much you've got, I think in Romania right now you have about 3,700 tons of used fuel. And so that's a goodly number of tons of fission products right there. So that brings us back to the beginning. So if we recycle, then obviously, as I said, this process uses much more of the fuel and needs huge amounts of energy. It's practical because the technologies to do this exist, and those technologies are relatively cheap. Moreover, we've been putting money aside for nuclear waste management. I think this is a wonderful way of managing nuclear fuel waste. So we can use those funds for this purpose. And what I like best, of course, is that in the process, you eliminate the million-year radiotoxicity. That's really very useful. So I would say, in conclusion, we should recycle used nuclear fuel. It's not waste. It eliminates the million-year radioactivity. And well, if you talk Romania, then from what you've got, you can already produce about $3.7 trillion worth of non-carbon electricity from the Bulgarian used CANDU fuel. We've got enough to produce $60 trillion worth of electricity. So I would say this is the way to go because it's non-carbon and there's enough in the world to produce fuel, which produces about $300,000 worth of electricity for every man, woman, and child on Earth. So it's huge, and of course it will avoid the elimination of the emission of nuclear I'm getting confused now of carbon dioxide emissions that are about 5.5 times the total carbon dioxide that's in the atmosphere right now. It's the way to go. Go nuclear. Thank you very much. I'd be happy to answer questions.
Thank you. So we'll open it up to questions. I put it in the chat as well. Anybody want to share any ideas, thoughts, remarks, or have a question for Peter today? It was a lot.
I have a question, Peter. I have a question for Peter, Heather. Sorin Epanovic.
Go ahead, Sorin.
Professor, thank you for presentation. I just want to challenge you, and because I have a question. We talk about producing the electricity, one of the topics here, which of course using the nuclear fuel and using uranium. But my question is, we use the same technology for a few 100 years, 200 years to produce electricity, which, you know what I mean, we have a boiled water, we use different type of fuel. We use gas, we use oil, we use coal to produce electricity. How about changing the way we produce this electricity using different type of fuel? Anything for the near future? Our engineers think about different technology to produce electricity. What do you think?
You know, I once upon a time worked on thermoelectric materials where you put current through the material and one end heats up and the other one cools down. So you might say if you use that sort of thing, you could reverse that and produce electricity from the temperature difference. It's like a thermocouple. So yes, but I think at the moment that's relatively inefficient. The other thing, of course, is that what we have in terms of the nuclear heat is about 2/3 or twice as much energy as we use to produce electricity, we produce as heat. And we're not using it at the moment. So you can make that very efficient by, say, heating buildings with that excess heat and so forth. So that while you're thinking of producing electricity, you should think energy, you know, in total. Certainly, you might say the sunlight uses the photon to create electricity, and that's a wonderful way of doing it. But you know, the sun doesn't always shine and so forth, and that's why I think nuclear is probably the way to go, because it has a tremendous amount of electricity per atom. It probably doesn't answer your question, but I try.
No, it's fine. It's fine. Speaking about efficiency, yes, indeed, nuclear, it's efficient. Hydro, maybe, you know, if we don't have enough water, we cannot produce electricity as we want. Solar, yes, but if we don't have enough solar, enough sun, also the electricity is not enough for our need. I talk about the humanity need. It means about the industry, our economies around the world, because you speak about trillions of watts of terawatts electricity produced in the world. But thank you for your question. Heather?
Great question. And you mentioned the sun. So
hello.
Yeah, can you hear me, Sorin? Maybe the technology is fading. We need more energy.
Yeah. Again.
Yes, I can hear you now.
I don't know if Professor is still with us.
He is.
Okay, maybe we have other questions from.
Yeah, the floor is open. Any other for any thoughts and ideas and questions about the future of energy and recycling the nuclear energy. I like the idea that instead of just finding ways to bury it, that there's possibilities of getting something out of it and having that be at a lower cost.
I just want to add one thing. You remember when the first plastics were produced and so on? They're producing the plastic and the plastic was never recycled and so on. So the same thing is happening with the nuclear energy. You know, you are producing energy, but you know, you have a lot of let's see, spent fuel, I will not call waste, that you need to have a process to recycle. It is not just the burying in the underground,
Right.
because nobody buried successfully any nuclear waste for the moment in the world. Everybody's experimenting. And there are a lot of materials which the professor didn't spoke about it, the the rare earths, which you can have it from the recycling of the spent fuel. And you know that the rare earths are used in the electronics, and it is very, very important resource. And actually the United States and China are they fighting now on the rare earths domain. You know, so I remember that I was in Afghanistan, and I know that in Afghanistan is a mine of rare earths, and nobody touched them. No the Taliban, no nothing, but the Chinese own that. And nobody talks about it. So the recycling of the spent fuel, it is a future, in my opinion. You know, you need to think, if you are investing some money in infrastructure, so you are investing money in some new jobs, you need to concentrate on the elimination of the radioactive, the long radioactive transuranic elements, which are for 400 million or 400,000 years or something like this. And you need to do something. For this one is the ingenuity of the humankind. You know, we invented things, and we need to continue to invent things, except politicians.
And the fact is that even when you bury it, you know, try to be out of sight, out of mind. It's never out of sight, out of mind. There will always be a result of some sort, even if we're not seeing it immediately.
We cannot do something which we cannot control. We cannot control Mother Nature.
Right.
And people wants to control Mother Nature, but they will never succeed. But what we can do is to eliminate as much as possible the bad things which are coming from things that we are producing. With the revolution, with the industrial revolution, we produce something, but we always have some residues, some problems, right? So we continually resolve the problems for the humanity. But if we are just watching, you know, and looking at the politicians who are absolutely incompetent most of the time, you know, you will not achieve anything. So the engineers are doing the progress in this world. So we need to continue to do that. So, and I think Professor Ottensmeyer very well outlined the ideas and the things which are common sense. Unfortunately, in our situation today, common sense seems to be lacking.
Right, exactly. And I like the way that you, and a lot of people are numbers people, they want to see the bottom line and what's it going to take to do all this, and pointing those numbers out of this is what, you know, it's not just burying it, it's all the cost that goes into that, the maintenance, the licensing, the land. I mean, all those other costs that, yeah, that you don't necessarily think about. And I think it's the job of all of us to take on of how can we use this recycled material and find new innovative ways, and there might be even more to come, things that we find that how we can use the byproducts of all
and you see,
of these things.
Strangely enough, they are speaking about the CO2, global warming, and all kind of stuff around, and they are not thinking about the nuclear energy, which is CO2 free, basically. So, you know, that I'm telling you, the common sense must be re-established in our societies.
Well, it all starts with discussions like we're having here today. So any other questions? I see a few people here with us still. Before we close out today, are there any final comments? Do you, Professor, have any final words of wisdom to give all of us with your presentation?
Well, I would say that I don't consider anything to be waste. Perhaps part of that is because I was brought up on grandma's farm, where we had horses and pigs and cows and chickens and whatever. And at the back of the barn, there was this big dung heap. You might call that waste. But in the spring and fall, we would load up a wagon of that stuff and drag
Use
it
it
out
for
onto
fuel?
the field. No, not fuel. It was basically fertilizer. And it took 3 horses to pull that wagon out there, and I had the pleasure of riding the 3rd horse back when the wagon was empty. So you might say I have a history of recycling.
Well, that's for sure. Yeah, actually, fertilizer is, keep our soil nice and great for planting. That's a whole nother discussion too. So.
But you basically take nuclear fuel and you make fertilizer out of it, which is all of those medium-sized atoms, and they are useful. They are, all over the map. And as Cornelio said, they're rare earths. I was pointing out the platinum group metals and so forth. So you can have your choice. I didn't know that the gases that were in there, the krypton and xenon, were so expensive, but I guess they have many uses in neon lights and whatnot.
Sure. All right, before we close, do we have any final comments from anybody? Okay, hearing nothing. I want to thank everyone for being here and for joining us. Cornelio, thank you for being here. And of course, Professor, thank you for joining us and educating us on the future of energy and the importance of utilizing all the things that we hold precious on our Earth. So I want to thank you so much and say have a wonderful day, evening, night, wherever you may be in the world.
Before you are closing, Heather,
Yes.
one question. This presentation would be available also for in the Facebook, and we can tell that if anybody is more interested in this one, to download the presentation at least without of,
Absolutely. Reach out to us with any questions. We'll have all these downloaded and then uploaded so everyone can continue to enjoy them, or just relearn and kind of process everything. Is a lot of information today, a lot of great information. So, yep.
Okay.
It'll be available and free. All right. Thank you, everybody.
Yes, and thank you for the invitation. It was my pleasure.
Thank you. Have a great
Professor.
day.